Welcome back to Fatch Math, where today we are going to continue talking about trig inverses. In this little video series, I did start explaining what regular or three most commonly used trig functions, what those look like on the unit circle. So sine, cosine, and tangent. You can see that work there. Or you can look back at the first video in this series, and then we pieced that together with why when we're dealing with inverses, if we're starting with an inverse, we have to consider that what we're given, the potential input, we can actually put it in our domain. All right, so we check that first. And then after that, we have to make sure that we consider our range when finding the side length or ratio of side lengths that goes with the, oh, I said that wrong. They give us, see, I say things backwards sometimes. They give us a side length or ratio of side lengths inside for inverses, and we're outputting our theta. That's the opposite of what it is for regular trig functions. Regular trig functions, you input that theta and you output that side length or ratio of side lengths. Now, why do I keep saying side length or ratio of side lengths? Because while sine is y, our height on our triangle, and cosine is x, our base. Those are side lengths on our unit circle, or on our triangle on our unit circle. Our tangent is going to be our ratio of y's over x's. That is super important, is y's over x's. That is going to look differently, because if you remember, we're going, oh, where's square root of 2 over 2 on the unit circle within the restricted range? What's that angle that goes with it? Well, tangent is a combination of x and y, so we got to do a little bit of background work. You'll get to where you're dealing with tangent so much, well, you'll be like, oh, at pi over 4, I know that square roots of 2 over square roots of 2 over 2 is 1. And you'll be able, and I say I just kind of did a little bit of number 9, but you'll be able to see stuff like that in your head. So let's go ahead and look at number 9. I'm going to bring it on down. I am not going to be doing all the videos, all the problems on the sheet, but I have produced videos where you're given one from each problem set. These are my little tracks from my other videos. I'm just going to come on down here and do number 9. Now I'm going to take that number off the front, and you'll see why here in a minute. I'm a very visual person. First thing I'm going to do, I need to make sure that I can actually plug 1 in, that potential input is actually in our domain for tangent. We'll go over here to our domain for tangent, and it is my favorite one. X is all real numbers. So that means that we can plug anything into tangent. Awesome. Well, remember, they are giving you a ratio of side lengths in this case, and we're trying to find a theta that goes with that ratio of side lengths. This 1 here is a sum y over x, all right? Let me write that like in blue or something. This 1 right here, that is, we are trying to find the y over x ratio that will give us 1 on the unit circle. All right, that will give us 1 on the unit circle. I do not like to think in terms of inverses. So I come in here and I'm like, I can take the tangent of each side of this equation to get this in tangent form. If you're one of my algebra students, my goal in algebra when you're solving for the variable is to isolate the variable. And you may be wondering here in pre-cal, why are we not isolating the variable? Well, I mean, it was isolated to start with, but we can actually, some of us can think in inverses very naturally. That's perfectly fine. But if you can't visualize that well in your head like me, and I'll be honest, I can't. I mean, I can, but not well. I like to write it down. Tangent of theta, we are trying to find the angle that gives us a ratio of side lengths that reduces to 1 on the unit circle. Well, lucky for us, we know if we're dealing y's over x's, we've got all those properties in mathematics that keep popping up that says if we have something divided by itself, this does not apply to 0. 0 divided by 0 is undefined because we can't have 0 in the denominator, but as long as whatever we're dividing is not 0, anything divided by itself reduces to 1. All right, so that's the goal. We have that property in mathematics. So if you saw my video where we were using the zero product property in order to help us solve quadratics, you heard me go off on a tangent. I'm on that joke today, or that pun, where I was talking about these properties are taught at the beginning of the semesters, usually in most math classes, from like 5th grade, 4th grade, all the way into high school. We're taught them, and then when they pop up, we don't really say, hey, this is when this is popping up. We are dealing with multiplicative inverse here when we're dealing with, if we're trying to find the tangent of 1. We know anything divided by itself is 1. And this looks a little different here. Just notice that if you're taking a and you're multiplying by 1 over a, that is a over a. Anything divided by itself is 1 other than 0. Super important there. So we are using the multiplicative inverse here to help us find the theta, the angle that will give us the ratio side lengths, that is 1. Using that fact, I'm going to go ahead and take off my markings here. And you're like, well, y's over x's. What are the only y's over x's that'll give us 1? Something over itself. It's not going to be this. It's not going to be this. It's not going to be this or this or this. None of these things are something divided by themselves. That takes a lot of solutions without even considering the range off the board. And then you'll see I skipped over these. We are dealing with a positive one. So even though the absolute value of these two numbers is 1, we've got that negative there that would give us -1 if we reduce. So we can't deal with quadrant 1, and we can't deal with quadrant 4 because those would give us negative ratio of side lengths, and we have a ratio of side lengths that's +1. So the only way we can get that is a positive divided by a positive, or a negative divided by a negative. Now, we're going to reduce this down even more. We got our 2 potential solutions already that's going to give us for tangent. 45 degrees might plug into tangent and give us an output, or 225 degrees, or we can say pi over 4 and 5 pi over 4. If you'll go back to the list of steps that we gradually developed together, like if you're my student, that's how it would have went, over our videos, we have to consider the restrictions on theta. That's the output of the original trig function. So that's the output of the original trig function. Looking here, you'll see that for tangent, we are restricted between -pi over 2 and pi over 2. If you watch my coterminal video, coterminal angles video, you'll know that -pi over 2 is the same as 3 pi over 2 on the unit circle. That is our starting point, and we can only consider thetas for tangent inverse that are between -pi over 2 and pi over 2. What does this mean? That means that the potential solution that we found down here in quadrant 3 is not actually a potential solution at all. We are restricted to quadrants 1 and quadrants 4 only here. Quadrants 1 and quadrants 4 only here. Well, quadrant 4, our tangent would be negative, so that throws that out of the equation, and that leaves us with quadrant 1. There's only one ordered pair that is something divided by itself, and that is this one. I don't like saying it because it's a lot of square roots. And then we've got in that ratio side lengths gives us the theta of pi over 4. So one of the reasons I like to write the steps for this video is none of this work is really shown. That's the thing that gets me. None of this work is really shown at all. A lot of it is done in consult this, consult that. Look, but our written work isn't really, there's not much there. That's one of the reasons I wrote it in the alternate form, so you could see how I was thinking about this. We're thinking backwards. If you're starting with a trig inverse and converting it back to its original equation, we've got to remember inputs in trig inverses are no longer thetas. And that's the defining thing here. I dropped my mouse and continued to talk, so that's what was going on there. This is math in which a lot of it is done by consulting resources, and the way that we consult those resources is guided by this series of steps. So we first have to make sure what we are given is actually in our domain. Then we consider the restrictions on the output. So when we're consulting the unit circle, it dwindles down our potential answers to our actual answer. Then we find the side length, if you're dealing with sine or cosine, or the ratio of side lengths, if you're dealing with tangent, that correlates with that, or we find that on the unit circle, then we find the theta that correlates with that side length or ratio of side lengths on the unit circle. Those are our 4 basic steps. And when we're talking about finding the side lengths on the unit circle, I do want to go ahead and specify there, because that can get confusing. This is our ordered pairs. Our ordered pairs on our unit circle are side lengths or ratio of side lengths, because if you watch my first video, there are a bunch of right triangles all over the unit circle, and we're dealing with base, height, and ratio of base and height. Well, there you have it. We have now learned effectively about how to use the unit circle to solve trig inverses by hand. Thank you so much for your time.